Okay, we're going to take a look now at some topics in Chapter 3, which deals with functions and graphs. Section 1, 3.1, Functions. Now, when we look at functions, one of the things that I think is significant is to note what is function notation. Well, we usually use the letter F. We usually put like an X there. And this is the function of X is such that, and then you give some example or a protocol to follow here. One of the things we did in the earlier sections was to say mx plus b, for instance. This would be in slope-intercept form if this were a y there. And another thing to remember is often when you think of function, you can substitute a y. Okay. Now, one of the things they want to find out here is what is the domain of something, and what would be the range of something. Well, let's just go back again for some background. If we had an ordered pair, x and y, the x elements would make up the domain, and the y elements would make up the range. So what we want to do is, in a particular function, what values could you have for x, and what values could you have for y? And another thing they're doing there is to ask you to what is a function itself. Well, by the definition, if you have ordered pairs, if the x element is only used once in a series of ordered pairs, we consider that a function. If the x value is used more than once in a series of ordered pairs, it's not a function. And that's what they're saying right here. Okay, now let's go on. Okay, I'm not going to read everything for you, but you can read it to yourself. So here are a few examples. Now notice they're not giving this in function notation, but they're saying this equation defines y as a function of x. So another way to write that would have been f of x equals x to the fourth. Now, are there any values of x that would make this statement untrue? And the answer is no. And you'll see as we go on and give you some other examples. So there are no qualifications here. X is, and we can put it in what we call set builder notation. X is such that X is any real number. Okay, let's go on. Now, when we write this, Sometimes it's written as I just gave you in set builder notation, and sometimes it's written in interval notation. And this is what it looks like in interval notation. We say this is all real numbers. It comes from negative infinity and goes to positive infinity. And whenever we use infinity, we use a parenthesis to enclose it. All right, let's go on. Now, as we look at example B here, here's where we will find that there will be qualifications. Because in order for this to be a real number, you cannot have a 0, or I should say a number less than 0, such as a -1, under the radical sign, or you can't have a negative value under the radical sign. So how do you go about determining what the domain of this would be? Well, you take away the radical sign and you just go x minus 6 is equal to 0, because that's the smallest value it can be. Can't be less than 0. Could be 0. So when you solve this, you go x is, just transpose the -6, becomes a +6. So you then say, well, x can be greater, I guess I can put that there too, or equal to 6. X is greater or equal to 6. Now, if you have a number smaller than 6, like 5, then you would go 5 minus 6 is a -1. So you cannot have in the domain of this function that x could be less than 6. It has to be greater or equal. And I explained the rationale for it. So what would the interval notation be? Well, let's look at it on a number line for a moment. Now we said it could be a 6, and 6 would be included in the set. And you put a bracket to indicate that 6 is included, and then you darken this line. That indicates the numbers continue to positive infinity. So putting this now in interval notation, you put your bracket, you put a 6, and then positive infinity. And remember, infinity always has a parenthesis to enclose it. The bracket indicates that the 6 is included in the set. Now let's take a look. And again, this operation will give you a value that has to be non-negative. Can't be less than 0. So this is what we've done. And there is our interval notation as we have explained it. Now, how about something like this when you have a fraction? Well, when you have a fraction, again, in order for it to be a mathematical operation, we can't ever have, let's say, 1 divided by a 0. If 1 is divided by a 0, this operation is undefined. So whatever value would make that denominator a 0 has to be excluded. So in solving for this, we just equate this denominator to 0, and we get x equals a -3. Well, if x is a -3, that would make this denominator a 0. So how do we write this? Well, we would say then that x in set builder notation is such that it's any real number, but cannot equal a -3. Because if x has the value of -3, it makes this denominator a 0. And then in interval notation, this one's a little bit tricky. Again, it's coming from -infinity, going up to -3, just this side of it, and then with union on the other side of -3 starts and goes to positive infinity. So they're showing that here, and they didn't put the symbol for union in there. They're using the word for union. The word is or. Let's continue. These are meant to be short reviews, and they don't give a lot of examples, but they're going over the theory. So in section 3.2, we're going to do graphs and functions. Now, again, one of the useful things I think will be important is setting up your graphs. And a tool for this would be a t-chart, where you have your x value, and your output can be, again, indicated by y, or often the function. And you're going to choose various points. You're going to perhaps have a negative value. You'll have a positive value. You'll have other positive values. And again, if you're going to make a straight line, you only need 2 points, 3 for sure. But if you're going to do a curve of some type, whatever it is, you're going to need 4 or 5 or 6 points that you plot so that you can sketch the curve. Now in MATLAB, they make that easy for you by, plotting a couple of points, and then it knows, in a sense, once you do that, where the others would go, and it forms it nicely. Okay. So here's our first one. Graph the absolute value function whose rule is defined by this. So again, you want to make a t-chart, and notice that your values will be of a positive x and a negative x. This is what they're showing here. And when you do your positive values, you get, let's say, x equals 1. then what does y equal? 1. If x equals a negative 1, again, since it's a positive value, it will be a positive 1. So as you continue to get lines, it looks like so. So this, and again, taking notes on this, pausing the tape as needed, is going to be very, very useful to, whenever you see a rule defined by this is the graph of this. When you see a graph like this defines the absolute value. Okay? Now, since they don't give us a lot of examples, let's take a look at this condition. Now, suppose here, instead of just saying that it's this, and you had something like this. That instead of it being just plain x, we're going to get that value of x and multiply it by 2. So here, if x were 1, this would be a 2, so this would be up here. Had to do a little sneeze there, and this would be a negative 2 over here. And if this were 2, then this would be a 4, and this would be a 4 there. Now, notice what's happening to our line, and I think this will be very useful going forward. That as you increase the value over here, the lines come closer to your y-axis. Now, if it were a 3, it would come up even closer. And then a 4, even closer. And the lines get closer to it. So we're just anticipating a little bit of the kinds of things we're going to see when we have absolute value. Now, let's take a look at the domain of this as well. What would the domain of this function be? Well, the domain, and in a sense, you can think of this going off to infinity for x values this way and this way. So it would be from negative infinity to positive infinity. And how about the range? We haven't done that, but we will be doing that. And these are for review. Well, actually, I get to change the symbol there. 0 is included in your y values. So this will start then at 0, and 0 is included in the set. That's why I used a bracket instead of a parenthesis, and go up to positive infinity. So again, we're trying to give you a little more background than perhaps what is shown here. And a test to determine whether something is a function or not is what is called the vertical line test. And let's go back here. And give you some background. They're not giving us a picture here, so let me pause and give you a picture. Now, in the vertical line test, this red line here, it's very thin. I'm going to move this vertical line over my graph that I've drawn here in black. Now, as this vertical line comes over this, which happens to be, let's say, y equals mx plus 2, is this a function? And we denote a function by the vertical line that we're passing over the face of the graph only intersects in one spot at a time. And yes, so this is a function. How about this? Yes, this is a function. And this is your absolute value graph. How about this one? This is negative slope. And yes, this is a function. How about this horizontal, which would be like y equals 5? Does this pass this vertical line test as we move this red line over the black line? Does it intersect only once as you move it across? Yes, this is a function. So these are sort of our main ones, and then we have this one, which is x equals, let's say, a negative 3, this black line. Does this pass the vertical line test? And the answer is no. So it's not a function because it intersects an infinite number of places. Okay, so some good notes would be useful. All right, our vertical line still. Is this a function? And the answer is no, because it intersects there and there. So this is not a function. How about your typical parabola? Does it pass the vertical line test? And the answer is yes, so this is a function. How about a sideward parabola opening to the side? And again, it intersects in more than one place. So it's not a function. And this wavy line, again, as long as it only intersects in one place, is a function. Okay, I'm going to wrap this up, keep it to about 23 minutes. And this is a little review of sections 3.1 and 3.2.